Okay, well, thank you for the introduction and to the organizers for the invitation. So I'll be talking about astrophysical sources for LISA, and this is a huge topic for just 15 minutes. So let me go straight to the point. So if you have to retain one slide from this talk, it will be this one. So you all know what LISA is. So it's a Michelson interferometer trailing the Earth around the sun. And because of the fact that we're in space and because of the large distances between the spacecraft, we can probe frequencies which are below what is achievable on Earth. So we're talking about frequency from 10 to the minus 4 to 10 to the, maybe to the frequency of Hertz, 10 to the minus 1 Hertz, say. So there are a plethora of sources in this frequency band, and they're all active at the same time. This is why when we talk about LISA data analysis, we talk about global fits. So we are pretty sure that there will be a few supermassive black holes, at least a few supermassive black hole binaries in the data, from a few up to hundreds or even thousands. Extreme mass ratios spirals, they're, as the name says, they consist of a stellar origin black hole or a neutron star orbiting a supermassive black hole. So these are, the rate is highly uncertain, so it could go from 1 to thousands. We know that there will be a few resolved galactic binaries, which we see already in the electromagnetic spectrum. So these are called verification binaries, but on top of those, as we heard in the last talk, we'll also have thousands of resolvable white dwarf binaries, which will be in the LISA band and which will constitute a foreground for other sources. In fact, there will be millions of these sources, which will be unresolvable and will provide, if you want, a background or a foreground according to what you're seeking. On top of this, we also know that some of the LIGO sources, LIGO Virgo Cagra sources that we observe, especially the more massive ones, will be seen as multi-band sources in the LISA band. So they will be in spiraling in the LISA band, emerging in the LIGO Virgo Cagra band. And also in LISA, we will also see the background of these sources. If we take the current rates from LIGO Virgo and Cagra and extrapolate them back to frequencies of millihertz, this turns out to be detectable and again constitutes probably a foreground if you're interested in cosmological or primordial signals, none of which of course is guaranteed. So in principle, the LISA data analysis is a very tough problem. So it's an inference problem in several thousands of dimensions in principle. So this is so now I will focus on the first of these classes of sources because it's the most important one. And hopefully I'll have time to say something about also the rest. So why do we believe that supermassive black holes merge? Well, for a start, we know that galaxies merge, or actually this we see in the sky, but also from the lambda CDM model, we believe that dark matter halos form hierarchically. On the other hand, it's an observational fact that each galaxy, or in essentially virtually all galaxies in the low redshift universe host a black hole, and the properties of these black holes are correlated with the properties of the host galaxy. This is the well-known M sigma relation, scaling relation between the sigma or the velocity dispersion of the bulge of a galaxy and the mass of the black hole. So these are quantities that live in two completely different scales. The black hole, of course, lives on sub-milliparsec scale, whereas sigma lives on the scale of kiloparsec, essentially. So this is a very surprising observational fact. But if you merge, if you combine these two facts, you come naively to the conclusion that because galaxies merge, also they contain supermassive black holes must merge. This is in a nutshell why we believe that these sources do exist. Of course, we have other evidence now from the compelling evidence of a stochastic background in the PTA, by the PTA experiments, but this is the theoretical explanation. The physics is quite interesting, or at least I find it quite interesting, because as I was saying, the relation between massive black holes and their host galaxies is one between two different scales. So on the one hand, the black holes talk to the large scales by injecting energy into the surrounding medium, and this is what we call AGN feedback. And on the other hand, the black holes feed on the gas contained in the nuclear regions of the galaxies. So this is a crucial fact to explain essentially the fact that all the stellar population live in the most massive galaxies, which is not obvious in the lambda Steinem model without the effect of supermassive black holes. So this is why the evolution of black holes is intertwined with that of the host galaxy. So it's a two-way street from large scales to from small scales to large scales, and from large scales to small scales. Okay, so this is all quite hand-waving. We also have, however, some evidence that these mergers do exist in nature. This is, again, one of these scaling relations that we often observe for black holes and nuclear star clusters. Nuclear star clusters are, as the name says, clusters of stars which are very compact, a radius of order kiloparsec and mass up to 10 to the 7 solar masses, which live, again, in the center of most galaxies in the local universe. And if you plot the mass of these nuclear star clusters versus the sigma, the velocity dispersion of the bulge that contains them, you see a nice scaling relation, at least for astrophysics standards, which breaks down at sigma of about 200 kilometers per second, or if you want, at 10 to the 6, 10 to the 7 solar masses for the nuclear star cluster mass. And the reason why this is expected is that we believe that supermassive black hole binaries actually erode these nuclear star clusters by what we call the slingshot effect. So the picture here is that supermassive black hole binaries do form and they eject stars from nuclear star clusters. And if you correct for these effects using numerical simulations and body simulations, you can reconstruct what would the scaling relation between nuclear star cluster mass and sigma would have been without this effect, and it turns out to be a very nice power law. So this is, if you want, fossil evidence that massive black holes merge in nature. There is, so when it comes to what kind of astrophysics we can do with LISA, the main dichotomy, or one of the big science cases for LISA is whether these supermassive black holes that we see today in the local universe are born from light seeds of about a few hundred solar masses, like the biggest black holes that we've seen in LIGO Virgo, or as heavy seeds, 10 to the 6, 10 to the 5, 10 to the 6 solar masses, which could come from a long list of possible processes in the relatively early universe, redshift larger than 15. Now, the recent detection of little red dots by JWST, these are very high redshift sources at about redshift 6, which are believed to be active galactic nuclei, and also the compelling evidence of a stochastic background by pulsar timing arrays seem to prefer this second formation scenario. So, but LISA will be able to settle this dichotomy for good, or maybe find that there is a mixing between these two, which is also very likely. The other big question mark when it comes to the detection rate, or if you want the astrophysical formation rate of these sources for LISA, is what we refer to as the final parsec problem. So we heard about this already. So even though we know that massive black hole binaries reach down to separation of about a parsec, because there's a plethora of effects, main one being dynamical friction and stellar hardening, taking them down to separation of about a parsec, it's very hard to make supermassive black hole binaries to shrink down from parsec separation to milliparsec separation, essentially because the reservoir of stars that can give rise to hardening, or if you want to slingshot effect, gets easily depleted. And and you need a way to replenish this reservoir of stars. So this was a problem that was understood, well, almost 50 years ago by these people in the early 80s. But it's a problem that still worries us today. And this is another topic on which LISA will shed light. There is, of course, a clear solution to this final parsec problem. If all binaries in the universe were to stall at about parsec separation, eventually you would form naturally triple or quadruple systems, because simply black holes keep accumulating because the host galaxies keep merging, and that we know happens. And when you form triple systems, as as people studying already solar system dynamics understood back in the 60s and 70s, you produce secular exchanges between eccentricity and orbital inclination. So essentially, what happens is that by way of this Kozai-Lidov mechanism, a three-body system develops eccentricity. So this is a numerical simulation, post-Newtonian three-body simulation of a supermassive black hole binaries at separation of about a parsec, plus a third intruder supermassive black hole, which is falling towards the central binary by dynamical friction and then stellar hardening. And as you can see, as the third black hole shrinks, the inner binary develops eccentricity. And this is conducive to mergers, because when you produce high eccentricity, you produce high bursts, very strong bursts of gravitational waves at periastron, and the central binary eventually merges. The important thing for LISA is that if this is the preferred way to solve the final parsec problem in nature, it means that we will have very large eccentricities, even a 0.99 at entrance in the LISA band. So this is something to keep in mind if you're a waveform modeler, because there are no such waveforms, to my knowledge at least, even though there is a lot of ongoing work on this in the LIGO context. Okay, so let me go straight to how many of these systems we observe. We have several models for the mergers of supermassive black holes in the LISA band. And one way we can test these models nowadays is by looking at pulsar timing arrays. So this is a summary plot from this paper by Boris Goncharov and collaborators. And they took a number of astrophysical models and looked at the predictions for the characteristic amplitude of the stochastic background in the PTA band. Because of course, these models, if they work, they must work for PTA before they work for LISA, because they're the same. Supermassive black holes are I mean, even though in PTA and LISA they have different masses, they're the same, they have the same formation scenario. So you can see that by and large, not all models are allowed by the data, but some are. So in the next slide, I will focus on, well, some of these models which I happen to work on, and consider only the models that are in agreement with pulsar timing array, we shouldn't say detection, but compelling evidence for a signal. And as you can see, in 4 years of observation, you could have anywhere from tens up to thousands of sources. This is somewhat dependent also on the seeding model. So as I was saying, most of these models are heavy seed models, except for a few. So in the case of heavy seed models, essentially LISA would observe all the population of supermassive black holes in the universe, whereas in the case of light seed models, some of these sources would be right in the band of the C-Hertz detectors. Yeah, so this is, if you want, the take-home message. Tens to thousands of sources, and the mass does depend on the seeding model, but with a preference for heavy seed scenarios. How about extreme mass ratio in spirals? Yeah, I'll go quickly about this. So people always ask how many MRIs do we expect, because they're a relativist's favorite source. Unfortunately, yeah, the answer is we don't really know. This is, again, from some work I did many years ago now, but I don't think the status has changed very much. So there are 12 astrophysical models with different assumptions. I can I can explain what the different assumptions are, but the bottom line is that you have from 1 to thousands of sources during the LISA observations. So one important thing that's, so why are MRIs so interesting? Well, because they carry also the potential to test general relativity and also to interact, and they also interact very strongly with their gravitational environments. We expect about 10% of MRIs to live in gas-rich environments, such as AGN disks. And these AGN disks could affect the in spiral of the MRIs and be visible at the level of single sources and possibly be degenerate with deviations from GR. Yeah, so maybe let me go to, because I only have a couple of minutes left if the chair allows me. So how are we gonna do astrophysical evidence, astrophysical inference from LISA data? As I mentioned, there are at least 5 classes of sources that are all active at the same time, and it's an inference problem in several thousands of, in tens of thousands of dimensions in principle. This is the global fit problem. So one approach that we tried recently is to use what we call simulation-based inference. So what we tried to do was to reconstruct the properties of the population of white dwarf binaries in the LISA band by performing forward simulations of parameterized astrophysical models, producing the LISA data stream or frequency stream, containing both resolved and unresolved sources, pass this to essentially to a neural network, to a normalizing flow, and then feed the LISA time series. So this is, again, the LISA, pass the LISA raw data, and we were able to invert the problem without extracting all sources, each source one by one. So again, we perform forward simulations of an astrophysical population, given some parameters, and we then use normalizing flows to invert this problem. So we don't perform a global fit, but we can try to estimate the properties of the population, the underlying astrophysical population, such as the mass function, parameters affecting the distribution of the sources in the galaxy, the number of sources in the data, even the noise parameters. So that these are some hyperparameters. As you see, there are several of those that we try to infer using both resolved and unresolved white dwarf binaries without performing a global fit. And it turns out to work quite well. These are posteriors produced by this normalizing flow machine that we employed. And as you can see, this is a conditional plot of the mass function conditional on the posteriors. So you see we can reconstruct the mass function very well, and we can reconstruct also the other hyperparameters of the population, again, without performing a global fit. And I think if you're interested in the astrophysics of LISA sources, this is an approach that might be generalized to other source classes. So I'm afraid I'm out of time, and I think I have to stop here. I'm happy to take questions about the topics that I didn't cover.
Any questions?
The models? Yeah, it was too fast. No, so you're talking about these models? Yeah, these models clearly solve the final parsec problem because we have a lot of mergers. So what we do here, we model really the formation of galaxies, including the baryonic components, including star formation, the loss cone replenishment, and the presence of gas, which is also conducive to mergers, the presence of triple systems. So in fact, for each of these events, I could tell you what the probable eccentricity is. And so, yeah, we do model both hardening, triple interactions with other black holes, and gas-driven torques. Yeah, so, and this is how the final parsec problem is solved. But there are uncertainties in this because we cannot simulate from first principles, not even supernova explosions, as we learned in the last talk. So supernova, for instance, are a key factor in the evolution of supermassive black holes because they exert a feedback on the bulge, which can quench star formation. There are many uncertainties. And so, yeah, so you should take these estimates as with a pinch of salt.
Okay, Thank you. So I have a question about the fossils of major massive black hole mergers.
Yeah.
Can you go to that?
Which slide?
Fossils.
The seeds.
No, not this one. Fossils. Fossil.
Sorry, which one? I didn't understand what. The fossil evidence. Yeah, sorry, the nuclear clusters. Yeah.
So I was not able to figure out how it's related to the final parsec problem. So is the methodology used here independent?
No, yeah, okay. So if you want this argument, guarantees the black holes make it down to separation of parsecs because this is the scale of nuclear clusters. They may not merge at all. So yeah, so you're technically right. So this only guarantees that black holes make it down to parsec separation. Well, okay, maybe fossil is not should help with that. Because, so essentially, yeah, this is the scaling relation between mass of nuclear star cluster and sigma that we would have expected. So, and this is what we observe. And we believe, based on modeling, that this, sorry, yeah, look, yeah, okay, well, you look at the points only. You see that there is somewhat of a power law. This is log scale, power law, and then the scatter increases. So this increased scatter is interpreted as due to the mass lost by the nuclear star cluster to black holes. And if you correct for that, if you consider only the subset of nuclear star clusters whose mass is measured dynamically, which are the golden standard, and correct for this effect, you find that you find a power law, as you would expect. So physically, this is due to stars which are ejected because they interact with the black hole and they exchange momentum.
Okay, let's break for the coffee now.